Hey y'all, welcome back. On tonight's homework, we're treating integrals as series as we try to evaluate definite integrals exactly. So we learned about Riemann sums as a way to approximate the area underneath a curve. And then we talked about in our last lesson how if we increase the number of subintervals to infinity, we'll get closer and closer approximations. And assuming we can go all the way to infinity, we would get the exact area underneath the curve. So let's just jump straight into the homework problems here. Number one says Ruth rode her bicycle on a straight trail. She recorded her velocity in miles per hour for selected values of t over the interval 0 to 2.4 hours as shown in the table below. Velocity is always positive. A says use the data in the table to approximate her acceleration at time t equals 1.4 hours. Show the computations that lead to your answer and indicate units of measure. So notice here that 1.4 is not in the table. So we're going to have to use the data points right around 1.4, which would be, wrong one, 1.2 and 1.6. So 1.4 would be like right in between there, right? And if we're trying to find her acceleration is the derivative of velocity. So acceleration is the slope of velocity. And so all this is really asking us to do is to find the slope in between these two data points, 1.2, 17.2 and 1.6, 16.3. And if we find the slope between those 2 points, that will be a good approximation of the acceleration for any time in between 1.2 and 1.6. All right, so we're going to use our good old-fashioned slope formula here. 16.3 minus 17.2 over 1.6 minus 1.2. Now 16.3 minus 17.2 is going to be, what would that be? Negative, certainly, negative 0.9. And 1.6 minus 1.2 would be positive 0.4. As far as the units are concerned, since time is measured in hours and velocity is measured in miles per hour, the acceleration should be measured in miles per hour or miles per hour squared. So this is a perfectly fine answer, although if this question was given as a multiple choice item, this fractions would be simplified. So just for exercise here, if we've got 0.9 over 0.4 and we're trying to reduce this or simplify that fraction, 0.9 is the same thing as 9/10, and 0.4 is the same thing as 4/10. 9/10 divided by 4/10 would be the same thing as 9/10 times 10/4. 10 divided by 10 is 1, and so this would reduce to negative 9/4. So you could leave it like this. You could even turn it into a decimal if you want. I guess that'd be what, negative 2.25. But either way, if it's a free response item, I would just say leave it here. And actually, taking it back a step, I would even leave it like this. If it's a free response item if this is a free response question, you don't even have to do the arithmetic. Just make sure you do include the units. It says show the computations that lead to your answer, and that's what I'm pointing to here. Those are the computations you need. Part B says using correct units, interpret the meaning of the integral from 0 to 2.4, so that's going to be that whole table there, in the context of the problem. Well, we talked earlier a few days ago about getting a clue as far as what the units would be at least, and then that can help inform our interpretation. When we find the area under the curve, generally we're thinking base times height. And so if we think about these units, miles per hour and hours, and we multiply those together, hours being like our base and miles per hour being our height, the hours are going to cancel out and we're going to get miles. Okay, so we are going to approximate this, but the units of whatever this thing's going to equal is going to be miles. So that's a little hint as far as like what it's going to represent. And we've talked about this on several problems before. The interpretation here is going to be the displacement between 0 and 2.4. But we'll get a little bit more specific once we actually compute it. Okay, so we're going to approximate the integral from 0 to 2.4 using a midpoint Riemann sum with 3 subintervals. So let's take a look back at the table. Our intervals are going to be from, well, let's see here. How many entries do we have? 1, 2, 3, 4, 5, 6, 7. So yeah, we're going to go from 0 to 0.8. We're going to go from 0.8 to 1.6, and from 1.6 to 2.4. Those are going to be our 3 intervals. So looks like the base on each of these is going to be 0.8. Just double checking there. Yeah, 0.8 is going to be the base on each one, and the height will be determined by the midpoint. So the height for the first rectangle will be 11.8. The height for the second rectangle will be 17.2. And the height for the third rectangle would be 16.8. So this will equal, or at least approximately equal, 0.8 times 11.8 plus 0.8 times 17.2 plus 0.8, again, one last time here. Make sure I get the decimal in the right place there, times 16.8. Now, if they really want an exact answer here, they're going to give you a calculator. They're not going to make you do this arithmetic by hand. I'm actually just going to leave this here. It's going to be this many feet. Okay, you could throw that in the calculator if you really want to know. It's probably going to be like, not feet. I'm sorry, miles. It's going to be, I would guess, I don't know, somewhere in the 30s, 40s, maybe 50. It's a little hard to tell. But you could throw it in the calculator if you wanted to. But it's that number of miles. And what this represents is Ruth's displacement from t equals 0. What are our units here? Hours. To t equals 2.4 hours. Basically, Ruth rode her bicycle and ended up whatever this number is. I almost want to put in the you know what? I'm just going to throw in the calculator so I can make a sentence here that sounds meaningful. Let's see, 0.8 times 11.8 plus 0.8. There we go. Times 17.2 plus 0.8 times 16.8. It's going to be 36.64. So it's Ruth's displacement from 0 to 2.4. And if we want to really just communicate like we're talking English here, we can say Ruth rode her bicycle 36.64 miles away from where she started. From time equals 0 to 2.4. Again, I'm happy with this top explanation, but if you just want a little bit more detail and maybe have a statement that is a little bit more meaningful, this second statement kind of does the trick there. Okay, there's number 1. Let's take a look at number 2. It says a twice differentiable function W models the volume of water in a reservoir at time t, where W is measured in gigaliters and T is measured in days. The table below gives the value of W prime, so the derivative of W, sampled at various times during the interval between 0 and 30 days. Okay, at time t equals 30, so on the 30th day, the reservoir contains 125 gigaliters of water. And part A says the tangent line approximation to W at time t equals 30 to predict the volume of water W in gigaliters in the I think we're missing a word here. Yeah, I think there's a typo here. I'm guessing it's just supposed to say like find. And I think that'll make a little bit more sense. You know what? I take that back. I think this should say use the tangent line approximation to W at time 30 to predict the volume of water in gigaliters, the reservoir. Okay, so what we're given here, and again, W, let's write this down. W is in gigaliters. T is in days. So W prime is in gigaliters per day. And so what it's asking for us is to first come up with a tangent line approximation to W at time 30. Let's do that first. And to come up with that tangent line approximation, we're going to need a point, and we're going to need a slope. So at time 30, so T30 is going to be 30 comma, and then what is the value of W at time 30? That's not given in the table, but it is given as the last sentence of the prompt. So it would be 30 comma 125. The slope of W, okay, this is for W, by the way, is at 30 is given in the table, 1/2 or 0.5. So the tangent line approximation would be y minus 125 equals 1/2 times x minus 30. That's going to be the setup, although I'm going to change these variables to match the context of the problem. Instead of x, I'm going to use t, and instead of y, I'm going to use w. So if I'm trying to use this tangent line approximation to estimate the amount of water in gigaliters at 32, t equals 32, I'm just going to substitute 32 in for t and solve for w. So I've got w minus 125 equals half of 32 minus 30. 32 minus 30 is 2. Half of 2 is 1. So I have w minus 125 equals half of 2 is 1. 1 plus 125 would be 126. So we can say that there's approximately 126 gigaliters of water at time equals 32. Okay. Part B says use a left Riemann sum with 3 subintervals indicated by the data in the table to approximate the integral from 0 to 30. Okay, so we're going to approximate the integral from 0 to 30 of this w prime. And we're going to use a left Riemann sum. The first interval is going to have a base of 10, so 10 times the height, and since it's a left Riemann sum, we're going to use the left number, which is 0.6. Okay, that's going to be the height of that rectangle. And really, I should say approximately here, not equals. Make sure our notation is accurate. And then our next interval is going to be from 10 to 22. So from 10 to 22, that difference is 12. So the width of that rectangle is 12. The height of the rectangle, we're going to use the left-hand side, which is 0.7. And then plus, the last one is going to have a width of 8 and a height of 1. Okay, so let's go ahead and compute this. 10 times 0.6, I think this is doable without a calculator, so we're going to go ahead and do it, is just 6. 12 times 7, I can do a little quick math over here. 7 times 1 is 7, so it's 8.4. And then we've got plus 8. So we have 16 and 6 is going to be 22.4 gigaliters. Okay. Yeah, great. Now, let's see what the follow-up question here is, because I don't think that was it. It says use this approximation to estimate the volume of water in the reservoir at time t equals 0. So remember, these integral functions are like, you should think of them as accumulation functions. So what this number represents is how much water, or how much water was accumulated. Okay, in other words, how much water did the reservoir gain from t equals 0 to t equals 30? So you have like the amount of water at 0 plus the amount that we just gained, 22.4, and that's going to equal how much water was at 30. Time equals 30. Now they told us how much water was in the reservoir at the end of this scenario. It was 125. So we can use this to find the amount of water that was in the reservoir initially at time 0 by just subtracting 125 minus 22.4. And let's see. Oh, that shouldn't be too bad, because 25 minus 22 is just 3, so it'd be like 2.6. Yeah, so it'd be 102.6 gigaliters. And that's how much water is in the reservoir at time equals 0. So this problem is actually a pretty important one here. This is going to lead us into our next unit. So I don't want to spend a ton of time on this, because we're going to have a lot of time on this in the coming weeks. But notice how we used the change in the amount of water and the amount of water that we had at one time to find the amount of water at a different time. Again, we use the amount of water at one time and the displacement, or how much water actually changed, the change in water, the accumulated water, to find the initial water. All right, that's enough for that one. Let's move on to number 3. Let f be the function given by f of x equals 9 to the x. If 4 subintervals of equal length are used, what is the value of the right Riemann sum approximation? Oh, and it even says this is a non-calculator problem on the AP test, so be ready to not use a calculator. That's okay, I think we can do it. So this is an exponential function, and if you're trying to visualize what's going on with this function, 9 to the x is going to do something like this. Okay, 9 to the 0th is 1, so this is at 1. 9 to the first power is 9, so this is obviously not going to be a scale, but just to give you an idea. And 9 squared is 81. So if we're going to divvy this up into 4 subintervals, the width of each subinterval will be 1/2 units. And which one are we using? Oh yeah, the right Riemann sum. So we're going to use this rectangle. Here's one. Here's the next one. Here's the third one and the fourth one. This is just a rough sketch. But we're going to have 4. So we're going to say the integral from 0 to 2 of 9 to the x dx is approximately equal to the sum of these 4 rectangles. Now, the width of each rectangle is 1/2. So we've got 1/2 times whatever the height is. We've got 4 of these. And so we just really need to make sure we've got the right heights on each rectangle. So let's do the easy ones first. Like the height of this second rectangle is going to be whatever 9 to the first power is, which is 9. So that's this one. This one's taken care of right here. The last one is also going to be pretty easy, because we know 9 squared is 81, so the height of that one's 81. Where we're going to really have to think is, what are the height of those other 2 rectangles? The first one is going to be 9 to the 1/2 power, And the second one is going to be 9 to the 3/2 power. So 9 to the 1/2 power, that's really just the square root of 9. So that's 3. 9 to the 3/2 power, well, the square root of 9 is 3. And 3, this is, if you're going to kind of really struggle, it's going to be with this one. So let me break that down. 9 to the 1/2 is square root. So this is the square root of 9 and then cubed. It's always power over root. So this is going to be 3 cubed, which is 27. Okay, now, dividing all these in half, it's going to be, it won't be super nice. None of these are even numbers. So instead of dividing them all in half, what I'm going to suggest is we actually factor out that 1/2 and do the addition first. I think that might be a little bit easier. Remember, no calculator here. So let's see if we can't pair these numbers up in a way that makes the addition a little bit easier. 3 and 27 make 30. 81 and 9 make 90. So we've got 30 plus 90 is 120. Right? So this is going to be 1/2 times 120. Half of 120 is 60. So our answer is C. All right, let's take a look at number 4. It says use the graph to determine each of the following integrals. So the first one is an absolute value function. And if we were just graphing the absolute value of x, it would look like this. Okay, the absolute value of x just reports back whatever the input was, but makes it positive. So it's kind of like y equals x, except all of these negative y values get reflected over the x-axis. And so you end up with this V-looking graph. Now, if I have the absolute value of x plus 1, then that plus 1 is going to cause a horizontal shift to the left. It's going to shift the left, try to make an F there, left 1. And so instead of this V-looking graph having a vertex at the origin, it's going to have one at -1 right here. So here's what the graph looks like. And once we get that graph down, we should be able to answer the question pretty easily. So we want the integral, or the area, bounded by the x-axis and the curve between -2 and 3. So -2 is right here. And then 3, well, let's see, 1, 2, 3 is going to be right here. So we really just need to add up the area of these two triangles here. This little tiny one right here, and this one right here. So let me erase all that just to kind of clean this up. And then, so yeah, this is going to equal the area of that first triangle over to the left. That tiny one is going to be half base times height. So half times 1 times 1. And then the second triangle, again, is 1/2 base times height. So 1/2 times 1, 2, 3, 4 is another 4x4 triangle. So we have half of 1, which is a half, plus, let's see, 4 and 4. 4 times 4 is 16, divided by 2 is 8. So yeah, we get 8.5. I'll just call it 8.5. For letter B, we have a linear function with a y-intercept of 0 and a slope of 1/2. So the y-intercept is not 1, it's 0, and the slope is 1/2. So I'll go up 1, to the right 2, and continue that pattern backwards. So my line is going to look basically like this, and I'm interested in the area between -2 and 4. Now be careful with this area over here on the left side, because it's below the x-axis. We're going to consider that area negative. So this little blue area down here is negative. This bigger triangle over here will have positive signed area. So this will equal the area of that small triangle, but we're going to call it negative. So -1/2 base times height, 1 times 2. And then we're going to add the area of that second triangle, the one that's a little bigger. It's got a base of 4 and a height of 2. So now we just need to pull together these computations here. Half of 2 is 1. So we have -1 plus 8 divided by 2 would be 4. Negative 1 plus 4 is 3. Number 5 has an integral from 5 to 5. Anytime you've got the left and the right-hand boundaries, anytime they're the same, you don't have to do anything. Okay, this is just always going to equal 0. You're finding an area of a shape that has no base, so it's going to have no area. Not really much else to say about that. Just be on the lookout for any problems where the upper and lower bounds are equal. Number 6 gives us an integral from 2 to 9. We don't know the function, but we know from 2 to 9 the area is negative 3. So it's asking what is the area from 9 to 2? And we know that anytime we want to swap the base, the bounds like this, we need to negate the overall area. So the integral from 9 to 2 of f of x dx will be the opposite of the integral from 2 to 9. Now the integral from 2 to 9 clearly is given. Okay, that's negative 3. So this will be the opposite of negative 3, which would be just 3. These next two questions are going to use the graph over to the left. It's got a semicircle and 2 line segments, and looks like we're looking for area here. So the first one's just asking for the area between negative 2, which is right here, and 2, which is right here. Kind of hard to see that, but basically we are looking for the area underneath that semicircle, this area right here. Now the formula for area of a semicircle is just half of the area of a circle. So this would be half of pi r squared, where r in this case would be 2. 2 squared is 4. Half of 4 is 2. So this is just going to be 2 pi. Now the next question is asking us to go from 0 to 5. So 0 is the y-axis, and 5, let's see, 1, 2, 3, 4, 5. Okay, so we're going to have to be a little careful here. We're going to want the area right here, this little quarter circle, which really should just be half of what we got previously. So we got 2 pi on number 7, so let me just go ahead and label this. This is just going to be pi units right here. Then we also want the area underneath right here, this little triangle here, but we will consider that area negative. So let's just start writing this out. So we have the pi, and we're going to say minus the area of that triangle I just highlighted. So half base times height would be half times 2 times 1. And then we're going to add the area of that other tiny triangle over here. And that'll be positive area because it's above the x-axis. This one right there. So that would be plus half of a base of 1, a height of 1. It's going to give us pi minus 2 times 1 is 2, divided by 2 is 1, and then half of 1 is just a half. So 1 half minus 1 is negative a half, so this is going to equal pi minus a half. All right, this down here was negative 1. This one is a half, so you can kind of see where all those are coming from. Number 9, we're just determining each of the following integrals. These are not definite integrals. These are indefinite integrals. So our answer is going to be not a number, not an area, but rather a family of functions. We'll write an equation, or an expression rather, with a plus c on the end. So we're just going to, looks like for the first few, just going to use that power rule backwards. And then with the last one, that cosine, we're just going to have to think back to what our trigonometric integrals are. So let's start with the first one. I'm just going to integrate one term at a time here. So this will equal x to the 4th. Okay, 4th times a 4 is just going to be 1, so the coefficient's just 1 there. Plus, it's going to be x cubed, and 2 times a 3rd is going to be 2/3. Plus, all right, so here we have 5 times e to the x. So that's just going to be 5e to the x. And then a plus c. For letter B, I think we'll want to distribute that 2x cubed first. So let's take care of that. And that would be 2x to the, I'm going to add the exponents here, 7th, plus 2 times 5 is 10, x to the 4th dx. And now we can just go one term at a time and find our antiderivatives. So we'll get x to the 8th, and then 2 divided by 8 is going to be 1/4, plus x to the 5th, and 10 divided by 5 is 2, and we need the plus c in the end. There's our integral. For c, okay, we've got the integral of 5 times cosine of x plus 3 over x. I'm going to think of that second term there. May not have to do this, but I like to think of this as plus 3x to the negative 1. And that's kind of what I'm looking for that natural log derivative. The derivative of natural log is 1 over x. So the integral of 1 over x is going to be natural log. Since the derivative of sine is cosine, we can say that the integral of cosine is sine. So this will be 5 times sine x plus 3 times the natural log of, don't forget these absolute value bars, the absolute value of x plus c. All right, number 10. We've got a differential equation, f prime, and we want to find the particular solution if f of 0 is negative 5. So first we're going to find f. So f is the integral of f prime. So we need to integrate f prime here. The integral of 6x is going to be, we'll start with x squared. 6 divided by 2 is 3. The integral of sine is going to be the opposite of cosine. And then we're going to have a plus c here. So to find that plus c, we're going to substitute in 0 and negative 5 into x and y here. So we'll say that negative 5 equals 3 times 0 squared minus cosine of 0 plus c, and we'll solve for c. So negative 5 equals, this is just going to be 0, minus, let's see, cosine of 0 is 1. So 1 plus c. Oh, missed a negative there. Negative 1 plus c. Then if I'm going to add 1 to both sides, I'm going to get negative 4 is c. So the particular solution, if f of 0 is negative 5, would be 3x squared minus cosine x, and instead of plus c, I'm going to write minus 4. All right, let's get into some series here, y'all. This is really what the lesson was primarily about. So I'm sure you were wondering when these problems were going to eventually come up, but here they go. Here they are. So let's go. Number 11 says write a limit of a series to represent each of the following integrals. So remember what we talked about in class, how what we're trying to do here is find the exact area under the curve. And we're doing that by adding up infinitely many rectangles. And so we use the series or the sigma notation because, you don't want to write plus blah, blah, blah infinitely many times. And so, yeah, we're going to have some sort of fancy notation to communicate the concept that we're trying to show here. So for the first one, we've got this natural log. And basically what we want is the area between 2 and 7 underneath that curve. So let's start with the limit. The limit as n approaches infinity. And basically what this is trying to say is, hey, we're going to have infinitely many rectangles. And we're going to add up all those areas, starting with the first rectangle and going all the way to infinity. And each rectangle is going to have a base and a height. The base of the rectangle will be 5, which is the difference between these bounds. Okay, so that's sort of like the total base, but we're going to divide that by how many rectangles there are. So we'll just say n, because we want n to go to infinity. So that's the base, and then we need the height. The height is going to be 2, which is where the lower bound is, plus 5 over n k. So basically what we're doing is we're incrementing one at a time. We're moving to the right 5 over n units. So if you're just trying to put all this together, and this is our answer. There's nothing more we need to do here. Okay, we're saying there's n rectangles. Okay, oops. Just going to make some notes here so we kind of put it all together. Basically, all this is always going to be the same. Okay, that is our way of plugging in infinity without plugging in infinity. The 5 over n, okay, that is going to be the base. Okay, it's the width of the rectangles, the width of each rectangle. And then the 2, this is going to be our like start point. Okay, so this is our lower bound. And then the plus 5 over nk. Okay, or let me just put it all, let's just put it all together. Might maybe easier to kind of think about this. 2 plus 5 over nk is going to be like the height of each rectangle. Okay, if you're wondering where the 2 is coming from, the 2 is coming from that lower bound. All right, now that's pretty much the setup. Okay, now let me be clear though, we don't actually have the answer here yet. We're very close, but this 2 plus 5 over nk, you're going to essentially replace your x with that. Okay, this is going to be the, this is going to be, mumbling over my words here, but that expression, you'll have a similar expression in all these, but that is going to replace the x. So we still need to take the natural log of that. So what I'm missing here is the natural log of that expression. Kind of got ahead of myself there. Well, I'm just going to rewrite it here. The natural log of 2 plus 5 over nk. Okay, so it's not just 2 plus 5 over nk, it's the natural log of that. So yeah, this is like your f of x. Okay, now let's see how that translates to b. I'm going to like leave these notes up over here just to kind of help us get the next one. So we want the limit as n approaches infinity because we want n rectangles. The more the better. The difference between the bounds is going to be 9. 10 minus 1 is 9. So this will be 9 over n. That's the base. And then the height is going to be that f of x. So it'll be 5 to the x power. But instead of writing x here, because I don't have any reference to x here, I'm going to start with the lower bound, which is 1. And I'm going to add 9 over nk. These problems look a lot scarier than they are. If you don't have a good conceptual understanding of what each of these pieces represent, it can be challenging and seem like there's like too much to memorize there. But I really want to emphasize the concept here, which is we are adding a bunch of rectangles, or adding the areas of a bunch of rectangles. And as long as you can like identify what the base and the height are, you should be able to get most of these right. Okay, let's do the last one. The limit as n approaches infinity of the sum from k equals 1 to n, And really, that's just the fancy way to say we're going to add up infinitely many rectangles. The base is, okay, the difference between the bounds here is 2 pi minus 0. That's 2 pi. So 2 pi over n times the sine of that, setup, that k setup, or that x setup. So we've got the lower bound is 0, and you don't really need to write the 0 there, but I'm just going to try to stay consistent with my notation, plus 2 pi over nk. All right, and that's all about it for tonight's homework. If you have any questions, please reach out, and I will be glad to help you out. But otherwise, you'll have a great day, and I'll see you next time.